So now we're going to talk about some principled ways of comparing factor solutions. And even these are a little bit messier than some of the stuff that we're used to when we do kind of statistical tests and stuff like that. They're still important to know about and know how to apply. So we have mostly focused on scree plots and parallel analysis and interpreting loading patterns for evaluating our models so far. However, we can use null hypothesis-based methods as well. So here, one issue is that it's a little bit backwards of how we tend to think about things, and this is something that I know tripped me up a lot when I first started learning this stuff. So it's worth understanding exactly what we're doing. So our null hypothesis when we're evaluating a factor model is that the covariance matrix, sigma, is being recaptured by the sum of the communality matrix and the uniqueness or specific matrix. And so the alternative hypothesis, of course, is that these are not equal to one another. So essentially, the alternative hypothesis is that the original covariance matrix is not equivalent to the sum of the communality and specific factors. So how is this backwards from what we usually do? So in this case, our null hypothesis is actually what we're trying to capture. In most cases, our null hypothesis is what we're trying to reject. But here, our null hypothesis is what we want to prove. And so this is when we want to try to prove a null hypothesis, we really can never technically do that, first of all. And second of all, it's also extremely narrow for when we want to do this based on some kind of test statistic using frequentist sampling distribution based methods. So while we can sort of get a p-value and we can theoretically use an alpha equals 0.05 cutoff, it doesn't really make sense because again, what we want is to prove that the null hypothesis is true. And so we're almost never going to get a p-value that's large for these cases. And even if we do, it still doesn't prove the null hypothesis. So we can still do this stuff though, and it is done sometimes, you will see it. So to test our null hypothesis, we're going to compare the covariance matrix implied by our factor solution, which I'm going to call sigma hat here, to our observed covariance matrix S. So this is a likelihood ratio test based method. So it's chi-square distributed with p minus m squared minus p minus m divided by 2 degrees of freedom. I think I'm good. Okay. So that's the likelihood ratio test for our for comparing our model implied covariance matrix sigma hat to our observed covariance matrix S. There's also a correction, Bartlett's correction, which is a slightly different approximation for the likelihood ratio test. So it replaces the n in n times the log of the likelihood ratio with this other kind of ugly thing, n minus 1 minus 2p plus 4m plus 5 divided by 6. Don't worry too much about it. This is the version psych uses. It's just worth knowing this is a slightly corrected version. So we can use this information to test the fit of our factor model. But in large samples, it's unlikely that any model is going to perfectly reproduce the observed covariance matrix. So we're almost always going to have a large chi-square, and we're almost always going to get a p-value that's above 0.05, which would lead to rejecting the null hypothesis. So does that mean we should just discard our model just because we rejected the null hypothesis? Usually not. So this result alone is a very, very strict criterion. It's gonna, we would almost never have a factor model if we use this as our criterion. And all it really tells us is that our model isn't likely to be strictly true. That this model isn't, perfectly reproducing the original data. It doesn't tell us that how good of a representation of the data is, just that it's not strictly a true model. And no models are really true. Another approach is to look for differences in chi-square values across nested models. So we can compare a reduced model with fewer factors to a full model with more factors. So we can test the chi-squared of the reduced model minus the chi-squared of the full model with the degrees of freedom equal to the difference between the degrees of freedom in the reduced and the degrees of freedom in the full model. But even here, our results are often going to be sort of more liberal than we want about how many factors we want to retain. It's often going to tell us that we want to keep as many factors as we can, as many factors that we have degrees of freedom for. Another alternative is to use these information criterion statistics. So the psych package uses what it's calling BIC, Bayesian Information Criterion. So this is an adjustment of the likelihood function based on the degrees of freedom, so that the statistics can be directly compared for different types of models. So essentially, this has a parsimony penalty. So for more complex models that involve more parameters get penalized based on BIC. You may also encounter alternative versions such as AIC. They tend to be very similar. The exact statistics are a little bit different. And so in practice, what you want to do is generally select the model with low information criterion. So the lower values here imply a better fit. And then you also want to use some subjective judgment about whether the model is sufficiently interpretable. This will tend to be a better approach to evaluating models than relying purely on like the chi-square tests and stuff like that. So the psych documentation has some kind of confusing information about how it's defining BIC, and it's not entirely clear to me how this aligns with the technical definition of what I know BIC is. It says it's one thing. I'm able to get the same values it's outputting as something slightly different. One way or another, I'm not too worried about exactly how it's computing BIC here or exactly what the scaling for it is. Just in general, lower BIC is going to be a better fit. Lower BIC is implying a better fit. So what we want to usually be selecting for is the model with lower BIC. So we can use the summary output to get lots of information about our model after we fit a factor model. And this is also where the advantage of maximum likelihood comes in, because maximum likelihood imposes these normality assumptions on the factor loading, on the specific factors and the communal factors, F and epsilon. So the results are more likely to follow a normal distribution and satisfy the assumptions of a lot of these statistics, like the chi-square statistic and the BIC stuff. So this is going to generally, as long as we can assume that our data is normally distributed, maximum likelihood is going to produce a little bit more reliable diagnostic information than the minimum residual or definitely the principal factor solution. So this is what the summary output likes. So you see you get sort of lots of different stuff from this. The main things to focus on here that we get are chi-square. There's a p-value over here that's cut off. It's always going to be tiny. Don't worry about the p-value. It's almost always going to say it's like 0 or less than 0.001. So we also get our degrees of freedom here. So it tells us our degrees of freedom. All of this stuff is accessible within the model output in other ways, but it's kind of hard to get at. The summary output is the best way to get to it. And then you also get BIC down here. So here BIC is 1.4. So those are the main things to focus on in the summary output. So here we see chi-square 30 is big, p less than 0.01. So this suggests we should reject the model, but of course we really shouldn't. What we really want to know is which factor model is best suited to our data, not necessarily which one perfectly reproduces the observed covariance matrix. This p-value is almost always going to imply you reject the null hypothesis. So it's really hard to interpret it directly. So let's compare to the 3-factor model. So we can use the ANOVA function to compare nested models. And so this gives us an output with lots of comparisons between them. It gives us the difference in the chi-square values. So this is the chi-square value for the 2-factor solution. This is the chi-square value for the 3-factor solution. Degrees of freedom are here. Here's the difference in degrees of freedom, which is just 13 minus 7. Here's the difference in the chi-square, which is the difference in the 2 chi-squares. This is the p-value for the difference. So here we're essentially rejecting the null hypothesis that the 2-factor model fits as well as the 3-factor model. And then we get our BIC values here. There's also a difference in BIC values over here, which isn't too important. Really what matters is that the three-factor model does have lower BIC. So that's often going to be the most interesting part of the output. Sometimes the nested model test statistic is also going to be kind of interesting here. But it is going to also tend to be pretty liberal about how many factors to include. BIC will tend to be a little bit less liberal. So this is, to me, slightly better evidence that the three-factor model actually is maybe better here. So here's how we can interpret the test statistic. The three-factor model fit the data significantly better than the two-factor model. And so just a little bit of explanation of where I'm getting this information. And then here's the BIC. So we can also look at a four-factor model here. Notice that we're getting really low on degrees of freedom. If we went to a five-factor model, we would run out of degrees of freedom and we wouldn't be able to do any of these tests. So essentially, we couldn't really interpret the results of a five-factor model in the same way, but we can with a four-factor model. As long as degrees of freedom is greater than 0, we can do all this stuff. So here we are, once again, rejecting the null hypothesis that the three-factor model fits better than the four-factor model, the p-'s small value. But probably more importantly here, the BIC is actually higher for the four-factor model than the three-factor model. So this is kind of evidence that we should probably not really worry too much about the four-factor model. So here's just the statistical results again. And really, given the BIC and the lack of theoretical support and the lack of interpretability of the factor solution of the four-factor solution, so the factor loadings aren't clearly interpretable in the four-factor solution, I really wouldn't even bother with it. I probably wouldn't even bother with the three-factor solution, honestly, even though the test suggested that it did fit better than the two-factor solution. The two-factor solution just had such a nice, clear, interpretable factor structure that I think that can be considered compelling evidence for the two-factor solution. Also, the fact that the three-factor solution was not reliably estimated across different estimation methods is also evidence that we don't really want to mess around with the three-factor solution. Remember, when we did the last slides, when we did maximum likelihood and the principal factor methods, we got really different results for the three-factor solution. So that's also evidence that it's not being reliably estimated, and we shouldn't pay too much attention to it. You can also use the little a ANOVA function to compare multiple nested models at the same time. So here we can do that. I wrote here that the test statistic is based on the first model entered, but I'm actually not 100% sure that's true. You can always tell which one it is based on the degrees of freedom difference. So here we see that the degrees of freedom difference is -7. So the first and second row are comparing the first and second model. Here it's 13. So this is actually comparing the second to the third model. So that's what this test statistic is. So that's actually wrong, and I will correct that. But that's how you can always tell. You can look at the degrees of freedom difference to see which model are being compared. So here, the degrees of freedom difference is 5, so it's comparing 3 to 4. So it looks like it compares each row to the previous row. So some takeaways on what we've done here. So unlike principal components analysis, which is again purely data-driven, and even some other statistical techniques that we've learned, there's a lot of subjectivity in factor analysis. These comparison procedures can be helpful, but they shouldn't really be used as like strict objective criteria on their own, the way we kind of do when we do significance testing in multiple regression or something like that. These methods won't always agree with each other. So like the scree plot didn't agree with the BIC approach and stuff like that. So you're going to get a lot of sort of conflicting information sometimes when you do factor analysis, and you really have to use your judgment about what information is the most relevant and really what information you should be using. And of course, we also want to make sure our models are sensible. So just because a test statistic says a model fits better, if the pattern of factor loadings is just nonsense, it's not a useful model. So it's really up to you to use the information you have to determine and to convince your readers which the best model is.